So much like when we started this problem, we'll pause and turn for a second. All right. Much like when we started this one, we started with, is there and was there a way to like create a timeline and have a method for figuring out and seeing what all the parts and the pieces were. And then we come to this one, and the first thing we had to remember, what consecutive meant. So again, this is going to depend on what age group we're working with. Integers is going to be a word that we're going to talk about today that you may not have heard for a long time. All right, so if you're working with younger students, you would say, give me 4 counting numbers in a row, right? And then what I heard another group talking about, just really verifying, having order of operations. So again, although not necessarily at a younger age, you could tap into this, and they're starting to get like, if it's subtracted from something, that meant that whatever the 3 things were that were added up, we subtracted away twice the first one. All right? And then and I heard a lot of groups doing this. And then you're like, well, what if it were 2, 3, 4, 5? And then you kind of walk through that. And then you realize, wow, that's not going to be anywhere close.
No, but I wanted to be able to have like a visual.
Yeah, to have a visual. Absolutely. And there is nothing wrong with being wrong. All right? We make the most mistakes when we learn the most. Now, sometimes people think that doesn't make, but it does. The research really shows that when you do something wrong in the learning process, you remember the right way better than being taught the right way and then trying to replicate the right way. When you get lost driving and you finally figure out where you are and get back, you're like, oh, I know what I did. Way better than just trying to, plug it into my phone and carry on and get somewhere that I don't remember how I got there because I followed the phone. All right? And then, if you're going to get more towards the algebraic side of things, if I have 4 consecutive integers, and some people say, all right, so we always love the variable x. So if my first variable is x, or my first value, my first number is x, with that in mind, think for a second, don't shout out loud. What's the next number if the first number is x? And there are 4 consecutive integers, and you're thinking and not saying it out loud. Like, what is the next number if the first one's x? I heard an O. Who did the O? What's the next number?
X plus 1.
It's x plus 1. So that's my next number in line. All right? And it's okay, now I've got another integer. And it's the next one in line. It will be x plus 2. And then my last number, so I'm going to erase this. Ooh, I didn't want to do that. I wanted to do this. There we go. I'm going to erase this for right now to have my 4 numbers. And then my 4th number will be x plus 3. And what I want to do is I want to, apologize on that one. I want to subtract, what did it say? Twice the first. So I'm actually going to be taking these, and I'm going to find the sum, which again, there's just a lot of math terms in here. So obviously this is not geared at a younger age, but you could say, if we put them all together, if we add them up, there's going to be other phrases that you're going to use in your classrooms. But if I add those up and subtract 2x from them, so I'm just going to kind of move that out of the way, that will be equals 16. And then we're doing our algebraic operations of 3x plus 6 minus 2x equals 16. Move your numbers around. And we'll do some algebra tiles later when we get through some more aspects of algebra. And we'll have a way that we're going to map that out and do it with a scale, because this is my balance point for my scale. And I have to be equal on both sides as I work through when I start doing some algebraic solving. All right. So with that, jump back to now, we're 1 week in. We've had several assignments and deadlines. Yes, within the 1 week side of things, if you didn't get 2 responses to the conversations that were happening, go back and do those. First week, there is some grace in that. So, yep, go back, do your 2 responses, because I'll have your first response, your post is due by a certain date, and then I think it was 2 responses due by Saturday. All right. And it's always hard if you're the first one, whoever's always the first person, right? Then you got to wait for everybody else to do it. And then there's the rest of you who are like, I'm like always the last person to get my first post in. And then it's easy. I can reply to everybody on the same day. There's different strategies to that. But yeah, go back, do that tonight. I'll go back and regrade. If you didn't get your notes in, get those in ASAP. I'll go back and regrade. That first week, I know there's just a lot of trying to figure out the rhythm because every class, every teacher, there's always different expectations and a different way that they go about it. And I understand that. I'm taking classes myself because I'm a weirdo. We are lifelong learners. I never stop. So we'll see what's after this master's if I do something after that. But, and it is. They're all different in trying to find that cycle and that rhythm, and you look at the calendar. So if you've missed something and you can still submit it, submit it. If for some reason online it says you can't even access that anymore, shoot me a little note. I'm not like super gifted in Canvas. I manage just fine. So that's how that goes. And next up, this is our agenda. So we'll go ahead and erase your boards down. You can shut the window screens down too so that you're not getting light on everybody's eyes. And then we'll jump into this. So this is some of what we're covering today as we go through this agenda. Mathematical reasoning, mindsets and reading, mathematical autobiography activity, which we already did. I don't know, I have that on there twice. We're going to look at other things that are due. We're going to work on a Math 1 domain today. If you did not bring a copy of it, don't worry about it. I don't ever worry about that kind of stuff. This is why technology exists. So we can just look at it online, work on a piece of paper, go from there on that. And I have it written twice. The second one was supposed to be, we're going to look at then the lesson planning. And I emailed you a template that you either can use in Word or in Pages if you're in the Mac land, that can be used to move forward. We'll talk about some of the specific aspects of that right at the very end of talking time. And then I'm going to pull out the box of manipulatives. We're going to start looking at them as you start to think, what do I want to do my little mini lesson on? And when I mean mini lesson, I mean like 10 to 15 minutes. All right, you're going to think through, but this is more getting you in the habit of saying, how do I write good learning goals? How do I look through the Common Core standards and connect what I'm doing to what it is in Common Core? How do I assess what I'm doing and know that what I'm doing is what I say that I'm doing and getting back to it from there? So, but this is just a reminder from last class. These are the domains. Today we're going to be talking about number sense. And we're going to start with a video. And let me see if it will let me. Nope. So yes, there's going to be much more to it. I didn't mean to show the video to intimidate you, but to give you some perspective on, we just get an opportunity to scratch the surface, and don't ever feel like I am inadequate, like I didn't get them. Listen, there's so much out there, none of us are going to get them to all of that. All right? So we find the parts and the pieces that we can capture with them in the classroom, and then begin. And when we get to lesson planning later, we'll be talking some about this because maybe your emphasis and your expertise is not mathematics, but finding ways to tie in with what's going on in another classroom. So the example I have, one of the many things I did as a math instructor was I always tried to figure out now this was going way back to when there was the analogy portion to the SAT, which was like, they got rid of that 15, 20 years ago now probably, but it was analogy, this is to, A is to B as C is to what? And so you had to try to pick amongst them what the different words were. And the English teacher always had these analogies, would have the vocab words. And so I just requested, could you just give me the vocab word for this, whatever grade I was working with every week? And they wanted to know why. I'm like, because I am going to use them in my lectures and in my conversations with the students. So they're hearing it in more than one place. And in terms of mathematics, if you're doing something that you're like, wow, that could totally be modeled by something that's a probability that they're doing in PE. You know, talk to that PE teacher about how, or if you are the PE teacher, talk to the math teacher or the English teacher about like, hey, what are some things that I can be doing that are going to cross-relate to what you're doing in the class? And then the students are like, wait, did you talk to them? Like, that's one of our words. I'm like, oh, that's one of your vocab words? Wow. Isn't that incredible? It's a good word. It really does, you know, it means something significant to what we're working on here. As you start, you know, and that's just like an entry level when you're looking at cross-curricular activities that you can do so that students know it's not a silo. You don't enter one room and it's one thing, you go to a different room, it's a different thing. We are doing it in concert with one another, or we ought to be in that process. Yay, Common Core standards, right? Here they are. Some of the stuff that's in domain 1, number, relationship among numbers, number systems. And then it outlines all sorts of different things that we have here, everything from fractions and decimals and percents, and we're talking about rational numbers. I'll show you a little flow chart on this here again, and trying to remember which the different ones are and how we set it up and what they're all different used for. We have things like the multiplicative identity. So 1 is the multiplicative identity. That's just one of those little concepts. Anything times 1 is 1. If you ever want to actually go into and figure out how to prove that, that's what the class on number theory was about. That he said this whole area of study is number theory. You start going, and what's the additive inverse, right? A plus negative a is 0. And what's the actual full proof of that? And yes, there's an entire study of, like he got to at the end, what are the axioms? What are the hard and fast rules that we have to have when we're going through this? All right, so for the most part, we're going to be landing in this area. We perform operations, positive, negative, fractional exponents as a way to apply whole and fraction numbers. That's what most of the maths that we're going to be working on in most of our classes are going to be about as we're developing understanding. And that will include then getting into geometry or geometric appreciation for some of these concepts. Computational tools, procedures, strategies. This isn't the Common Core. This is off of the State of California website for teacher credentialing, domain 1. I'm like, wait a second, candidates, yes, candidates. Demonstrate fluency in standard algorithms, fancy word for processes. All right, your algorithm is the process by which we go from beginning to end. For computation, we're going to evaluate correctness of non-standard algorithms because there's going to be other ways to do it that are non-standard. Demonstrating understanding of the order of operations. You may have learned it as PEMDAS. I always taught it as PERMDAS. We'll get there later. And demonstrating an ability to use technology. And now the word technology can be interpreted lots of ways. We're not saying cutting edge. You're using some new device that's out there, a new program that's out there. I mean, realistically, a protractor is technology because we're utilizing a tool to help us do something better or more efficiently, and that's technology. I'm not saying don't use online things and don't use the computers and don't use, I love using stopwatches because you can learn a lot about what's going on in the natural world with stopwatches, meter sticks, things along those lines for doing geometric principles and shadow lengths. We bring in water balloon launchers and you throw, send a golf ball vertical and tell the kids don't get hit when it comes down. And then time it and understanding, and you can actually calculate gravity that way. And you can do that as low as middle school pretty easily. There are software out there, and then there's obviously some more complex calculations that we might have to do. So what is number sense? What is mathematical fluency? That was the word map that we looked at. You're going to be engaged in these strategies. And it says flexible, efficient, and accurate to solve problems in mathematics. It doesn't start there. I mean, wouldn't that be awesome? You walk into your classroom and they're flexible, efficient, and accurate. That'd be amazing. I wish I was that every time I stepped into a room teaching and learning. All right? And it has to be more than memorizing. All right, we're in an age, and this will all depend on now you're going to have future instructors, and as you go out and work in the classrooms and work with teachers, you're going to have different approaches. My philosophy on formulas is this is why the internet exists. I no longer require students to memorize formulas, things along those lines. Instead, I even tell in most exams that I give and tell kids, go make yourself a study sheet and you can use it for everything. And if you have to have a formula on there, put it on there. If you need a formula and you forgot to put it on your sheet of paper and you come ask me, I'll give you the formula. Because it's about, for me, the procedures and the processes and deep critical thinking. And here's a formula, which in my mind is just another tool that gets you there. They're not at a place academically where they should be deriving those formulas. Maybe later on, high school, college level mathematics, you would assume that, well, if you don't remember it, you can get there. All right? We're not there right now. But to get fluency, students need to connect their conceptual understanding with those strategies. So some of the non-curricular tasks that we do at the beginning of class are doing that very thing, or ideally, finding ways to engage students. Some kids just find it fun. And again, I have no problem with that because they are doing some critical thinking. They're developing their own strategies, and in some cases, even their own algorithms to solve problems. That question that we did were the consecutive numbers, if you would have started 2, 3, 4, 5, and then 3, 4, 5, 6, and then you start noticing the pattern in that difference. And I don't know if that's how some of you did it. And then it doesn't take you long to jump to the numbers. Oh, wait, it's going up by this many or this many. And then, oh, this is where I got to get to. I got to get to the 5th pattern or the 6th pattern to get to that place. So they can come up with algorithms, and students are really good at this. I mean, if you've had your own children, you also know this. They have algorithms. They do certain things to get what they want. And they learn the most efficient route to that. And if you have buttons to be pushed, they know where they are and how many times they can push that button until certain things happen. All right? We are wired this way. God created us to be pattern perceivers, and we want to make sense of them. All right, so it's a form of intuition. Yeah, those students who do it, they develop, more of a holistic rather than a separate digits of view. Right? We want to allow them to see that math is integrated in all that they're doing. I mean, that's my opinion because I love mathematics and I see it in everything. Patterns, timings of things. Children's behavior is very predictable when you start learning more about brain development and growth. They're not hard to figure out for that. And then also realizing that until a much later age, they're not thinking, so you can just bypass the whole what were you thinking question. You never have to ask it because realistically their prefrontal cortex is not connected, so they are not thinking in a critical thinking standpoint. Yes, they're thinking, their brain is operating, but they are amygdala-driven little creatures. I like to say cherubs, but usually it's sarcastically. I love little children, and as long as they're with other people. Other people's little children. All right. Understanding how numbers measure quantities, and then they change, and then how they all fit together and they can appear. I'm a math teacher, not an English teacher, so a par apparently is not going to be spell checked for me.
English is hard.
Number sense reflects a deep understanding of mathematics, but it comes about through mathematical mindset that is focused on making sense of numbers and quantities. And that's out of the one textbook that you have, the Bowler textbook, amongst the many other things that they said. Pause. So, and this is where I want to pause. I've talked a bunch. I'd like to go not more than about 10 minutes of talking where I stop and let you process. And then usually people are like, what should we be writing down? Just like the notes, write down something that's reflecting. You're like, okay, that made sense. This isn't making senses. Making senses? Again, math teacher. What did you mean by? Those are the kind of questions we should be processing through for what this is going to look like for you, for teacher credentialing, towards working in that process and programs, or maybe in the other classes that you're taking, or some of you are in classrooms right now. And if you find hey, we did this, and where was that fit into the, starting to piece together, So what, and now what are my usually three top categories. The what is this. We read, we talk, we look at the book. And then we get to more the so what. So what does that mean? How do they connect to each other? What's the relationship that we're trying to identify? The now what is, how do I connect with that? How is this going to be meaningful to me so that it can be meaningful to the students? And maybe the so what is, and how do I need to get through all of this to get my credential in the least painful way possible? I'm sure you didn't decide to go into this because you wanted painful approaches.
I don't know, I do like to take the long way. I do like to take the long way through things.
Sometimes the long way is more scenic. Sometimes. So with that, are there things that you feel classmates might want to get an answer to or a point of clarification that someone might have missed?
Say that again, I'm sorry.
It's the standard way of saying, are there questions? But that's so another caveat. In the process of learning to be evaluated and evaluate others in the area of education, I was challenged one time by a colleague friend of mine who was teaching at the college level, and he paused and, are there any questions? And the person evaluating him didn't have a background in education. So he was a little put off by that. They just had a background in mathematics because they're a doctorate and they're working on research, but they're required as part of their job to come in and do an observation evaluation of him, of his teaching. He has his master's in education. He's got his master's in mathematics. Like, he's like, really? This guy's going to be asking me? But the question he was asked was, or what he was told was, don't ask, are there any questions? Why? The evaluator said, because it does one of two things, typically. You have to admit in front of all of your peers that you don't know what's going on. And that's the biggest thing. And the second one was lesser to that, but more along the lines of, if they really knew that they have a question, they probably already know how to get an answer to that question too. So you're probably not going to get those kids to respond. So instead you got to find out, how do I ask a question that's not, hey, are there any questions on what I just did? But I usually go with I talk fast. I slur my words together sometimes because I talk too fast. I misspeak often. And I'll put words in wrong orders as I go through that. And I'll say, I am positive I confused someone. How can I clarify what I just caused the confusion on? So I'm owning the confusion, not the students. All right, now, if I say it the same way every time, they start to go, just ask us if there's any questions. But I try to get them to, so it's, or after I'm done talking, I'll pause. I'll say, okay, now notes to your future forgetful self. Which means now write down some things that you were listening for and like, oh, I needed to write that down, but I didn't. I encourage students to not take notes while I talk so they can really listen and engage. And then I'll pause. If I'm not good at it, I set a timer. Or like an egg timer, right? Right. So the ding, oh, I got to stop talking. You need to write some things down. And then write questions for me. Like if you're writing down while I'm talking, writing down questions. And I don't know how you are as adults, but students are. If you don't write down your question, you'll forget. I won't forget. I won't forget, Mr. Stefan. You will forget. I guarantee you. Hand goes up, I can write it down. Oh, okay. I come back. I'm like, so what was your question? I don't remember. So writing down your questions allows you to own your own questions, which I may answer later on. Or come back to and say, no, don't forget this and remember that. And then like, oh, no, I had a question, but I wrote it down and you answered it. And I'm like, wait, did you write the answer down to your question? No, write the answer down too.
Too easy.
Well, they don't remember to. Again, they're not sentient beings really at that age.
I notice with my first graders, you can tell when something is making sense or when they're lost.
Yes.
Their face gives them away.
Yeah.
But I'm also guilty
we were about 2 minutes into the video, and a lot of people were like, okay, yep. Beyond anything I've ever done. I really, yeah. Like, I'll watch, I'll pay attention, I'll occasionally write something down so it looks like I'm paying attention.
Did anybody else think Big Bang Theory?
Well, in a way. You know, every whiteboard and background in Big Bang Theory is actual theory and math that's going on. And some people think, oh, it's all like theoretical physics. It's not.
No.
No, there's a lot of fun stuff that goes on in the backgrounds. And do I look for those things? Yes, because I am that nerdy and geeky. They're two different things, right? So with that being said, in this grand explanation, in what way did I confuse you? All right. Right there, because then So then these are some of the things that you might be addressing for number sense by grade level. All right? And if you're working with those grade levels, you might see those things happening. All right? TK to second grade, organizing, counting with whole numbers, comparing order numbers on a line. We did that today, didn't we? With time. And we took it beyond just ordering them, right? But there's a lot of things you can do to order things and getting them to think quantitatively. We don't say those words with the younger ones, but that's what we're doing. What quantity are we measuring? How can we organize? Let you read through some of those. Third through fifth grade, we start talking about making sense with operations, start working at fractions and decimals, working beyond and maybe outside of just whole number values, because not everything operates as a whole number value. A lot of cooking can go on. I remember my firstborn was in pre-K, and they had measuring cups. And they were using measuring cups to see how many of these filled that one and how many of these filled that one. And they were doing fractions. They had no idea, like, oh, this one takes 3 of these to fill it up. And so they were getting a conceptual understanding of fractions just by playing with sand or water or whatever it was that they had with the measuring cups.
We're going to do that tomorrow with our 4th graders. We're doing recipes.
Sometimes you work with a math nerd that likes to point out every time you use something that you hate.
Yes. Yeah. So number theory topics that we're going to talk about, base 10 number system, because that's what we operate in. There are different number systems, but the American system, we're base 10, pretty much most systems are. Adding, subtracting intervals, prime composites, factoring, positive, negative numbers, notation of even and odd, and then what is zero, divisibility, which gets back to factors, rational and irrational number systems and fractions. These are all topics that we'll touch on. What do I mean when I say base 10 numbers? I mean, we group things in groups of 10. When we think of scientific notation, something that you may or may not ever get a chance to work with, but it's all based on base 10 values, counting things up with our digits from 0 to 9. And then here's how it might look in a classroom. Right? We have 10. So these are base 10 numbers and these are base 1 numbers. So 10, and you can actually then, when you're working with them, overlay them. So see, like, okay, so 10 and 7 make 17. The back of the card has our dots, and then how we put them together to get them to think counting. I encourage fingers and toes if they need to. All right, we're made base 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 fingers. Ta-da! It's a fantastic method. And I've known, unfortunately, too many teachers who are like, why are you counting with your fingers? I'm like, I count with my fingers all the time. Use them. All right?
Put your fingers up, I say.
So we put it all together. Then we we expand this back out. So after we do the cards to get to bigger values, we take the bigger values and break them apart. 1,234. That's 1 1,000. That's 2 100s, that's 3 10s, and that's 4 1s. All right. When you get to a place where you might be teaching comp sci, and kids want to learn more about coding, which can happen in middle school, sometimes even late elementary school, Binary is the same way. People are like, binary. It's the same idea of how many things you have. It's just grouping and set theory going on. All right, so I've got 1,000. I have 2 hundreds. I have 3 tens, and I've got 4 ones. As we break things apart and put things back together for what does it look like? All right, and then how do we know this? How can we start comparing then those values as we move along? Again, that number ordering, number line system for how many we have of different groups. And then our family favorite is fractions. All right? Friday was always fraction day for me. No matter what level of academics I was doing, Fridays were fraction days. We're going to bring in fractions and do fractions of some type, and then marking them out. All right? So you can have little number strips like this that kids then actually make into eighths. You can do it by folding, putting in their lines. They see an eighth. You could even cut them up and then put them together or take them apart and seeing that that's 5/8 and this is 9/8. And then you'd be saying, okay, well, what if I wanted to do 9/8 divided by 5/8? Right? We're like, wait, how do I do division of fractions? I'm like, well, this 5/8 is right here. 1, 2, 3, 4, 5, done. Boop. And then I have this much left of this much. So I've got 4/8 of the 5/8. We're not going to go too far into it, but this is how we're going to be able to grab it. We're actually going to do a little simpler example of just dividing here in a minute. All right. How is the algorithm for addition related to subtraction? So algorithm is just our process. So thinking through, when you start thinking about subtracting, how are they the same in some ways? And if you can start getting kids to realize that adding and subtracting really are the same thing.
That's so hard for them.
Very hard to do, yeah. But if we don't get subtraction down, then subtracting negatives, and kids are blown away going, how in the world do I ever do that? And then seeing the algorithm for multiplying and how it's related to this, it's the same thing as dividing, right? Dividing by 3 is multiplying by 1/3. All right? Multiplying by 3 is dividing by 1/3. And always allowing some of those things to happen as you move along in that process. And then later on, when they start doing 2 negatives when they multiply, it really takes application when they get to physics. And they're talking about vectors and directions and multiplying of vectors. And if I have 2 negative vectors, I've changed direction twice. So I'm going left, then going back right. So I'm positive with my 2 negatives. All right, so it's missing the R. Did I show this last time we were here? It feels like I talk about this every class I take of every level I teach. Adding and subtracting, some people say they're opposites, or you can say they're the same thing. One is putting positive numbers together, the other one's doing something with a negative number with it. But they are the same, or they're inverse operations, however you want to think about it. Multiplying and dividing are inverse operations. Exponents, I don't have my inverse operation for exponent. Parentheses is a grouping tool. Everything else are math operations. This parentheses, that's a grouping tool. So I've got multiply, divide, add, subtract, exponent, and what? Roots. So if I square something, the inverse of that is square root. If I take the third power of something as an exponent, the inverse is the cube root. If I have an exponent to the half power, opposite of that is squaring it. So I like having the R in there. I don't find many other people. And I learned that during my student teaching from a teacher, a long time ago. But I was like, that's brilliant because it makes sense from a math point of view. There's an opposite, or there's an inverse operation that goes in there. So remembering things like this. When I'm adding, do I have to have common denominators? If we spend enough time with our fraction tapes and looking at it, kids won't need to have to be asked this question because they'll be like, well, wait, we can't do those combining because I'm talking about different breakups of the 2 different things. And like, I need to get them all broken up the same way if I'm going to start putting them together. Multiplying is getting to area where we don't need common denominators. But again, then developing the idea of, well, what is multiplying and what is going on, and having a graphical or an area understanding of fractions. I'm going to skip that one. So there are tons of videos out there to watch. So before I get this one queued up, we'll take a short break, let you go stretch, move around a little bit, get a sip of water, and then we'll come back and we'll watch this quick little fun video on wrapping math fractions. All right. So quick run back on this one. Natural numbers, whole numbers, all the different ways that we categorize these values. There's a little, not the best figure for it here, but we see this Venn diagram, this overlap of things. So natural numbers include 1, 2, 3. Then integers include the negatives plus these, well, and 0. So 0 is a natural number because you can have 0 of something. And then I have 1 of something. So natural numbers is, I say, well, what occurs naturally? Like I naturally can grow an apple, an orange. I can produce an human, right? I can't produce a half a human, all right? I can't produce, it should grow as whole values or as natural things. Integers then include the negatives. Rationals then get me to anything that can be done as a fraction is a ratio. That's why they're called rational. If it can be made as a fraction, it's a ratio. And then reals is all the other numbers that are in between all the rational numbers. Real algebraic and then real actual values. We start talking about pi. E is Euler's constant. He called it the exponential in the video we watched. All right. And then these two are what are called irrational numbers because you cannot, in any regular fraction, make the number e. You can't make the number square root of 2. That's a fraction of 2 integers. And then we add algebraic, and then we add the complex number system. If you ever went with that, you had I. I is the square root of -1. And then we actually do a lot more graphically with the complex numbers, which include, so that's just all these different things. But again, where do we spend most of our time? We're down here in the rationals, integers, naturals, whole numbers. We might dive into a little bit of these square roots, depending on the level we get to. And then coming up with a conceptual understanding of pi, measuring a circle and the circumference compared to the diameter. Doing it with Cheerios, and then doing it with something that's smaller, and something smaller, and something smaller. And you see as those ratios, they slowly approach that number that we know as pi. Again, getting them to appreciate the building of it. All right. Factors, greatest common factor we've talked about briefly when we talked about the number, the learning task we did last week with the tax collector. Right. Trying to reduce the number of factors that get used up when we take the one number in. All right, but when we talk about greatest common factor, factors are numbers. Let me just do this here too. I use these words a lot, so I always forget that not everybody uses all these words all the time, like I do. Factors and terms. Factors are things that we multiply and divide. Terms are things that we add and subtract. All right, so having good, clear language as we're working through this. When I'm doing things that are factoring, it means I'm dividing it or I'm multiplying it. So a greatest common factor, greatest, largest, common, they all have in common, something similar. Factor, something that can be divided. When you get to some pre-algebra and you start talking about adding like terms are things that are similar. Counting boys and girls in the classroom, how many of this do we have, how many of that do we have, and we put them together. A handful of coins from you and a handful of coins to me, I can only add the like terms. How many pennies, how many nickels, how many dimes. I'll have a total dollar value at the end, but the terms are the different denominations that are going into it. And then we find things using prime factorization. May have been a while since you've done that. All right. 18, 9 times 2, 3 times 3. So 18 is equal to 2 times 3 times 3, which as exponents is 2 times 3 squared. All right. So just looking, again, getting at some of these ideas that it may have been a while when we talk about prime factorization. Prime numbers then are only any number that's only divisible by 1 and -1. Again, last week, how do we get the most dollars out of it? And you can get kids to this idea of prime. So it could have been used as a tool for teaching prime numbers. Well, why was 11 a great choice? Well, because and what are other numbers that were good choices? These other numbers are good choices because the number 1 was the only one that could, all right, and then, so they all have that same common characteristic. And wow, when we have a whole bunch of things that are the same, can we give them special names? And we do, we call them prime. Least common multiple. Then when we get towards working with fractions, which we'll again do on our worksheet here in a minute. Additive identity, I touched on already. What number? So additive identity. A plus what value gives me A? And this is where the proof of 0 comes in. So my additive identity is 0. A times what number gives me A? A times 1. So the multiplicative identity is 1. And then we talk about the inverses of them. Additive inverses add to 0. Multiplicative inverses multiply to 1. Oh, that red on orange is not a great combination, is it? 1/3 times 3/1. I'm not going to sing the song, but when you multiply fractions, right? Multiply the numerator and the denominator. 3 times 1 and 3 times 1 is 3/3, which is 1. So multiplicative inverses multiply to 1. Additive inverses add to 0. Much like the additive identity was 0, the multiplicative identity was 1. There is a connection there. They all go together. There's a pattern to the mass and the mess. All right. X squared means x times x. Squaring is repeated multiplication, which means it's also repeated division. This number, whatever this is the base, and that's my exponent. I can have positive exponents. Negative exponents means whatever the base is to the exponent gets flipped to the other side. If I had 1 over x to the -4th, the negative means I flip it to the other side of the fraction to make it positive. And anything divided by 1 is just x to the 4th. So if you have a negative exponent in the denominator, it moves to the numerator. If I have 1 in the numerator, it goes to the denominator. And then fractional exponents, this is where we get to the whole of PERMDAS. X to the 1/2 is the way that we denote the square root of x. So fractional exponents are my roots. So if I'd have x to the 1/4 power, that would be equal to the 4th root of x. Or what number times itself 4 times is x. Don't freak out by this. These are just all the properties that go into exponents. So if this were a lesson you're working on and you're developing it, if I looked at this idea here, if I have same bases and multiply, I'm adding. So going to what I just said on the previous page, if I have times x to the 1/4 times x to the 1/4 times x to the 1/4. They have the same bases. I am multiplying. That means I will add them up. All right, going back to cooking, I have a 4th plus a 4th plus a 4th plus a 4th because I'm adding the exponents. I have 4/4, so I have 1. Which means x to the 1/4 to the 4th power, because I have 4 of them multiplying. Exponents are repeated multiplying. 1, 2, I'm multiplying it by itself 4 times. x to the 1/4 to the 4th, I just showed was x to the 1. But then that allows me to do this property here. Powers raised to higher powers, those multiply. I have 4/4, so 4 times a 4th is 1. Still gets me to this same example here. So in some quick practice, so what would this look like as we practice through what that looks like? Thinking, of course, always, always, always this. PERMDAS. There are no parentheses. There are exponents on the y. It has a negative exponent, which means I need to put it in the denominator. When it flips to the denominator, it's now positive. The z is in the numerator still because the power on the z was a 1. Looking at this next thing, most common mistake people are going to make in a situation like this is thinking that that -3 is also on the 4, and it's not. It's only on the x. So the only thing that moves to the numerator is x to the 3rd. 4 remains in the denominator. If it were, so this would be a new problem, if I had 4x to the -3, well, then everything that's the negative power would go to the top. And this then would be 4x to the 3rd over 1. All right. Now I have everything that's taken to the -3rd. 2 ways you could do this. Instinctually, a lot of us will go, well, this is then going to be 1 over all of that. And that's to the 3rd power, which is true. Another approach is to just do this, because I've now put everything that was in the denominator in the numerator, everything that was in the numerator in the denominator, because that's what a negative exponent does. It moves things to the other side. To the 3rd power means times itself 3 times. Again, there's a couple different ways you can approach it, and if I do it longhand like this, I get, yep, that's 3 times 3 times 3. I can write it as 3 cubed. 2x times 2x times 2x is 2x cubed. Or I can start simplifying and say, well, that's going to be 27. 2 times 2 times 2 is 8. X times x times x is x cubed. Ran out of space on the side of my slide right there, and it won't show. But there's a cubed on that x, just trust me. There, teeny tiny little one.
Stare at it till you see.
0 power. You might be thinking, well, how does that happen? Deriving it, which is normally what I start with if I'm working in a classroom. If I have 12 divided by 12, my exponent here is 1, my exponent here is 1. When I divide same bases, I subtract exponents. 1 minus 1. So this would be 12 to the 0 power. And then going back to this, 12 divided by 12, anything divided by itself is 1. So 12 to the 0 power is 1. X has a power of 1. Y has a power of 0. So it's 1 times x times 1, which is x. And the last one's a little more complicated because that's what we do. Now, I've gone through these way faster than I would typically do in a normal classroom setting. Variation theory is another process for teaching where you give them one little nugget that they probably know how to do. And then you change it just a little bit, enough that intuitively most students will go, oh, well, isn't that going to be this? And then do like a couple in that same process. And then you change it just a little bit, where they look at it like, oh, okay, that changes. And then they go, oh, and again, get them to a place where they can oftentimes work themselves up, building on just small, teeny, tiny variations every single time, so that when they get to the end, if I would have done it in 3 steps, I do it in 20. They're going to discover those processes. And sometimes on the boards, after we do our non-curricular tasks, we then have them go through a series of 20 steps where it's a little bit, and they go, oh, this is easy, Mr. Stefan. And then they're like, ooh, not as easy. Some might burn through them really quickly, others might take some time, but getting them to think about those next steps and do those next steps. So again, variation theory is what it's called. And we experience it in other ways. You go away from family and you come back and you see your little nephew or niece, and you're like, oh my gosh, they have changed so much in the last 2 months. And mom and dad go, I guess we haven't noticed that much of a change because we see all the little things. So we see the one point to the end point and don't realize all the hundreds of little steps that happened in that process to get there. If we can get students to do that, then they're going to learn and not even know they're learning. So we jump to the last one. Powers raised to powers. Well, let's look at this one. This is a negative. So that means I'm going to start by putting whatever is in the numerator, or whatever that whole thing is, a squared b to the 4th c, in the denominator, and I change the exponent to a positive 2 because it jumps to the denominator. The other thing is ab squared c squared stays in the numerator. Some people will be like, now I'm going to start to reduce. Can't do that until I eliminate my parentheses. And parentheses can be done either as, just move that over here so I got some more space. If it's small ones, I typically just write it all out. So my top will stay a times b squared times c squared. My denominator, I'll have a squared times b to the 4th times c times a squared times b to the 4th times c. Again, because squared means times itself. I like to reorganize them, put the common ones near each other. And then either remember principles of exponents or say, well, if I just take the a's here, thought bubble, right? In my head, a squared means a times a. The other a squared means a times a. So in the denominator, come on, move everything up again. So in my numerator, I'm still going to have a times b times c squared. And then I'll have a to the 4th, b to the 8th, c squared.
Did you get rid of the square somewhere on the b in the numerator?
It just accidentally disappeared. Typo.
Okay.
Yeah. So when working with, and that's a good example, I do that often. Because I get going and I'm like, oh, I want to get to the next point and teach the bottom part, and I will just totally forget a part over. I would like to say I'm just that smart that I do it to see who's paying attention. And if I'm with middle schoolers, I'm like, yes, good job. You should be always watching for my mistakes. I make them to see if you're paying attention. Right? Don't think that it's just me looking for mistakes on your paper. I want you to find mine too. Yes, sir? Yes, and if I make a mistake once and I continued my mistake, am I demonstrating that I don't understand what I'm doing mathematically? Nope, I'm demonstrating that I lost track of something. Just like your shoe,
It's so common for our kids too.
right?
Where did that
Middle school
my
student,
marker go?
where is your left shoe, middle school student? I don't know. I don't remember when I last had it on. And yet we want them to hopefully keep track of their exponents. So as I approach things from an academic side of things, and I talk to students about how do you grade things, right? Do you do partial credit? Like everything is partial credit. The life is partial credit. But if I made a mistake and that square disappeared and it stayed disappeared and I finished everything out the right way, you still have demonstrated you have a grasp of what we're doing, a pretty solid grasp. You just lost track of something. Not a big deal. I'm not testing on can you keep track of it. I'm testing on can you show me how you got to an answer that makes sense using the principles we've talked about. If you can, full credit, but I got the wrong answer. But did you? You got the right answer for the wrong thing you wrote down, but that's a right answer with right processes. So then we finish out principles, and again, this is where you could really go at and show, okay, well, my A, in the numerator, the exponent is 1, so when I'm dividing, going back to that slide that had the dividing, it'll be 1 minus 3. Others of you say, yeah, but there's more A's in the denominator. How many more? 3 more. Because this is supposed to be a 4. It's supposed to catch me on that. 1 minus, I already wrote down the answer. I'm like, 1 minus 3. I'm like, oh, it's 1 minus 4. It's negative 3. 1 minus 4 is negative 3, which is why I have a to the third in the denominator. B squared over b to the 8th. Some will look and say, well, there's just more in the denominator. How many? There's 6 more. But if I use the properties, it would be 2 minus 6. 2 minus 8. See, I did it again. And 2 minus 8 is negative 6. So it goes down there to 6. C squared over c squared. 2 minus 2 is 0. So I'd have c to the 0 or just 1. So again, this lesson plan, yeah, so this I cannibalized from Simpson. They're using it for a lot of their teacher ed. But what goes into a lesson plan? So this was the first page. There was a second page to it as well. But when we look at it, obviously the title, what subject am I teaching, what grade level am I teaching, and then your teacher's name. So what you're going to want to start thinking about as you're doing either this activity set or you look ahead to some of the other topics that we might be covering, pick something that you feel comfortable doing for a subject, all right? And then what domain am I hitting on, all right? So we've got the 4 domains that we've been that I've shown in the last week and then this week, one of those first couple slides. And again, the slide decks are online. You can look at those again. And then you're going to identify what Common Core learning standards are being addressed with that particular domain. So this is going to take a little work, getting in there. And realistically, this is why Google exists. Which Common Core standards are taught when I'm figuring out lowest common denominator? And it'll probably spit out to you all the Common Core standards, and then you can read through them and decide, oh, which one am I using? Learning objectives. This will be then stretching you if you've not done a lesson plan. Students will know and be able to do as a result of the lesson. All right? It can't just be students will know something because you don't know that they know. They need to be able to do something with it. So learning students will be able to articulate something. So then your assessment would be, all right, further down. Your assessment for what they're going to be doing, maybe it's on the second page, is how are they going to articulate that? Are they going to have like a little exit slip that they fill out on their way out? As you walk around, you're going to ask them to explain it to you. What specifically measurable outcome are you going to be able to assess on a daily basis? To know that they know. Because we can't just do they know it? I don't know. I can't read their mind. Good thing, right? We don't want to be able to read other people's minds. So when you're writing a learning objective, just getting a couple 3 in here maybe. If you've done lots of lesson planning, then go at it and just have fun. If this is the first time you've ever thought about all these things, keep it simple. Have just 2 learning objectives for a 10-minute lesson that you're going to do on whatever subject you pick in whatever domain you choose. All right, learning objectives stated in student-friendly vocabulary. So now it's today I will. Because part of a lesson is also having your outcomes or your objectives on the board so the students know what they're doing. It gives them a roadmap, much like I did at the beginning of class. Today we're going to cover these things. Just so you know, that's where we're going. For this, it's on the side of your whiteboard. Maybe it's something that you have on a slide when they walk in that says, here's what you are going to do today. Today I will. So go, this is what I'm going to do today. And the students are saying, I'm going to do these things. These are the same. It's just here, students will. Here it's they're going to say it. And maybe here it's said in more educationese. And here it's more relevant language to whatever age group you're dealing with, whatever grade you're talking about. What activities and tasks are you going to be doing? Listing any resources, textbooks, manipulatives. And then the last thing is then how do you know that you've met these outcomes, these objectives? I always call them outcomes. So objectives, it's the same idea. What's my objective? What outcome am I looking for? And then how do I assess that? How will I know that they know? But more importantly, metacognition, how do they know that they know? So your assessment at the end, I'm not talking like quizzes and tests. It can be a very simple thing where they're doing something, they finish the task, they have their whiteboard display of their final solution with probably all their mistakes written. It's something that they can do to say, wow, and then you go back to the objectives. And the students say, I will be able to today, I will. And the kids go, oh yeah, I did. Not I will, I did. And it's going to be a past tense thing because then they've reached that. So just our introductory level to what a lesson plan is going to look like. So as we're working on this, as you're thinking about some other math topics, maybe you've seen a math lesson that you've done in the past or been witness to in the past. So you're like, I want to try to find a way to recreate that. Start using this document, start plugging some things in. In another probably week and a half or 2, we're going to start sharing it with a group that you're going to be assigned to. And then so that you can see how someone else is writing it. It's not so that you can go, oh my gosh, that's so much better than what I did. It's so you go, they're doing it differently. And they might be very different and all both okay. Because there's a lot of ways you can go about doing some of these things. And yes, again, Google exists for a reason. Now, I don't recommend doing the teacher pay teacher thing because you can get a lesson plan on anything that's out there. But that's just paying someone else to do your work, which do that later. Right now, we want to see that you can actually learn it. You didn't hear me say that. Or be that teacher who puts all their stuff out there and you get paid, right? There's a lot of people that are creating content for this sole purpose who are really good at creating content. But you can go online, or Chat GPT. A lot of teachers are getting into that. If you've not created your own account for AI, I recommend it. I do it all the time, where I'm looking for progressively more challenging questions and assessment questions for the students' t-distribution in an introductory statistics class. ChatGPT go. And then they pick one of them, so I'll take one of the questions they ask. I said, now make it so that this and this and this. So I'm like, and it'll generate, give me 10 questions. It'll generate 10 progressively harder questions for me. Great content. And then you can get really creative and say, based on 1990 census data, right? Or really pick something nuanced there that you want to touch on. And then I'm not creating it. It's great. This is the benefit of AI. A lot of teachers have started using AI to create lesson plans, right? But you have to be intelligent about how you're telling ChatGPT to do it.
It will literally do what you tell it.
It'll only do what you tell it to do. So if you want it to connect to California Domain 1, Common Core Standards, this, and this, give me an easy, medium, and hard question to introduce a topic on, so again, if you're like, I don't know where to start, but you know the questions to ask, this is how AI is going to be really beneficial for us in the education field, so you're not having to create them all the time. Now, you're going to get something that's going to kick out at you, and you're going to go, this was terrible. Absolutely. Much like a calculator, if I don't plug the numbers in right, I'm going to get a wrong answer. If I don't put in some questions that make sense in ChatGPT, I'm not going to get a response. And there's other AIs. I just say ChatGPT because that's the one I have up on my laptop right now because I've been doing some work on it. But that'll be the task that we're working towards the end. I want to show this to you. I sent this to you as an email attachment so you can, if you already know where you want to start going, start plugging things in there. We did not finish this document today, so I will build time in next week so to make sure that we actually can get through any other questions you might have, to make sure we get it completed before we get into the next thing. So, as I mentioned, this is my first time doing an evening in 3 hours, and I feel like I'm already cutting a lot that I would really want to do, but that's because I want to help you so badly. So I'm like, I have so many things I want to tell you, and now I just got to realize I got to cut some things out. So my apologies that we ran this late and you didn't finish that document. Don't worry about finishing it on your own.
Do we turn it in? Like
Nope, but you're not going to turn it in, but we will look to see that it's done, and we say, yes, we did it. Collaborative access to it. We've completed it. I want to know that you understand the parts, and what I hear in conversation has been very good. This is what I would love to see happen in any school-age setting. It won't be. Maybe it will be. You'll have that one day where you're like, oh my gosh, this was the best day of teaching ever. Today I retire. But no, we're not going to be actually turning that in.
So what do